A complex system is a system that exhibits some of the following characteristics: feedback loops, some degree of spontaneous order, robustness of the order, emergent organization, numerosity, hierarchical organization. A complex system can be also viewed as a system composed on many components which may interact with each other. In many cases it is useful to represent such a system as a network where the nodes represent the components and the links their interactions. Examples of complex systems are Earth's global climate, the human brain, social organization, an ecosystem, a living cell, and ultimately the entire universe. History. Although it is arguable that humans have been studying complex systems for thousands of years, the modern scientific study of complex systems is relatively young in comparison to conventional fields of science with simple system assumptions, such as physics and chemistry. The history of the scientific study of these systems follows several different research trends. In the area of mathematics, arguably the largest contribution to the study of complex systems was the discovery of chaos in deterministic systems, a feature of certain dynamical systems that is strongly related to nonlinearity. The study of neural networks was also integral in advancing the mathematics needed to study complex systems. The notion of self-organizing systems is tied up to work in non-equilibrium thermodynamics, including that pioneered by chemist and Nobel laureate Ilya Prigogine in his study of dissipative structures. Types of complex systems. Nonlinear systems. The behavior of nonlinear systems is not subject to the principle of superposition, while that of linear systems is subject to superposition. Thus, a complex nonlinear system is one whose behavior cannot be expressed as a sum of the behavior of its parts. Chaotic systems. For a dynamical system to be classified as chaotic, it must have the following properties. It must be sensitive to initial conditions. It must be topologically mixing, and its periodic orbits must be dense. Sensitivity to initial conditions means that each point in such a system is arbitrarily closely approximated by other points with significantly different future trajectories. Thus, an arbitrarily small perturbation of the current trajectory may lead to significantly different future behavior. Complex adaptive systems. Complex adaptive systems are special cases of complex systems. They are complex in that they are diverse and made up of multiple interconnected elements, and adaptive in that they have the capacity to change and learn from experience. Examples of complex adaptive systems include the stock market, social insect and ant colonies, the biosphere and the ecosystem, the brain and the immune system, the cell and the developing embryo, manufacturing businesses, and any human social group-based endeavor in a cultural and social system such as political parties or communities. This includes some large-scale online systems, such as collaborative tagging or social bookmarking systems. Topics on complex systems. Features of complex systems. Complex systems may have the following features. Cascading failures due to the strong coupling between components in complex systems. A failure in one or more components can lead to cascading failures which may have catastrophic consequences on the functioning of the system. Complex systems may be open. Complex systems are usually open systems, that is, they exist in a thermodynamic gradient and dissipate energy. In other words, complex systems are frequently far from energetic equilibrium. But despite this flux, there may be pattern stability. See synergetics. Complex systems may have a memory. The history of a complex system may be important. Because complex systems are dynamical systems, they change over time, and prior states may have an influence on present states. More formally, complex systems often exhibit hysteresis. Complex systems may be nested. The components of a complex system may themselves be complex systems. For example, an economy is made up of organizations, which are made up of people, which are made up of cells, all of which are complex systems. dynamic network of multiplicity as well as coupling rules. The dynamic network of a complex system is important. Small world or scale-free networks which have many local interactions and a smaller number of inter-area connections are often employed. Natural complex systems often exhibit such topologies. In the human cortex, for example, we see dense local connectivity and a few very long axon projections between regions inside the cortex and to other brain regions. Recovery and failures of complex systems. A complex system can evolve into spontaneous recovery and failure and have hysteresis behavior, may produce emergent phenomena. Complex systems may exhibit behaviors that are emergent, which is to say that while the results may be sufficiently determined by the activity of the system's basic constituents, they may have properties that can only be studied at a higher level. For example, the termites in a mound have physiology, biochemistry and biological development that are at one level of analysis, but their social behavior and mound building is a property that emerges from the collection of termites and needs to be analyzed at a different level. Relationships are nonlinear in practical terms. This means a small perturbation may cause a large effect, a proportional effect, or even no effect at all. In linear systems, effect is always directly proportional to cause. See nonlinearity. Relationships contain feedback loops. Both negative and positive feedback are always found in complex systems. The effects of an element's behavior are fed back to in such a way that the element itself is altered.